Alright, this lecture is about electronegativity and bond polarity. Well, what do we mean by electronegativity? Well, I'm going to tell you right now, if you remember that fluorine is the most electronegative element, you'll be golden. Here's my rough outline of the periodic table. Here is fluorine. So, why do I say this? Well, if fluorine is the most electronegative, it means as you go up the rows, or up your column, it's going to become more electronegative. And similarly, as you go across a row, it's going to be more electronegative. So let's say you have hydrogen and you have oxygen. Which is going to be more electronegative? Well, the oxygen is, because it's going to be closer to fluorine. The closer you get to fluorine, the more electronegative of an element you're going to have. So, as you go across row, you're going to become more electronegative. And that's just going to be abbreviated electronegative from here on. Now, why is this? Well, as you go across the row, the nucleus is going to have more protons in it, with the valence electrons being approximately in the same orbit. So, let's just draw this out really quick. These are going to be my protons, and here's going to be my electron orbit. As you go across the row, the electron orbit's going to approximately stay the same. You're going to increase a little bit as you add more electrons, because each orbit can only hold so many. But generally, as you go across a row, you're going to increase protons. So let's say oxygen is going to be right about here, and nitrogen is going to be right about there. So with oxygen and nitrogen, as you go from nitrogen to oxygen, you gain a proton. And 4, I'm just representing a small number. As you gain more, the electrons are going to be closer to the nucleus. There's going to be a bigger positive charge in the nucleus, meaning that it's going to want to hold on to these electrons a little bit further. It's not going to want to give up these electrons. And as you go to fluorine, it's going to be the most, because you're going to have the most positive charge with the closest electron shell. That is why fluorine is the most electronegative element. Now let's look at why, as you go up a column, it's more electronegative. Well, why is that? Well, this explanation is not as easy. You don't just gain electrons, which means that the attraction between the shell and the nucleus is stronger. In this case, your shell is getting bigger, and you're gaining more protons. So, wouldn't it make sense that once you're down here, you're going to be in the 70s, 80s, 90s, and that means you're going to have 90 protons in a molecule. Once you have 90, that nucleus is going to be very, very positively charged. So why isn't this the most electronegative? Well, this drawing right here is not very representative. If the protons were actually this big, as I've drawn them, my electrons are going to be clear across the other block. It's going to be hundreds and hundreds and hundreds of feet away if the protons were this big. So in this drawing, as we gain more electrons, as we go down the column, we get more protons, but our electrons are also going to be very, very, very far away from the nucleus. And as you get farther away, you're going to be getting more rows of electrons. So here's our valence shell, the very furthest shell of electrons. I might just draw in a few pretend electrons. You're going to have shielding. It's called shielding. You might have learned this in basic chemistry, but what it comes down to is all of the electrons that are in these rows are going to take some of the charge away. There's going to be a little bit less attraction between these positive protons and these electrons, just because they're so far away and there's so many electrons in between that there's just going to be a little bit less of an attraction between your furthest electrons and the nucleus. So, shielding is one. Another reason is because the valence electrons are just simply further away from the nucleus. With every row that you go down in your column, so if you go down your column, down all these rows, as you go further down, the electrons are going to gain even further distance away from the nucleus, meaning that there's a further distance between the positive charge and the negative charge, and as I've said earlier, you're going to have less of an attraction. So I'm just going to say that's distance. So shielding and distance. Those are the two effects of electronegativity. So now, let's put this into use. Talking about all this is okay, but let's put this into an actual example. What does this actually do for us? Well, when you know the electronegativity, you're able to figure out the bond polarity. Of a molecule, and between single bonds. So, in our example, here's going to be our molecule. Now, this is going to be a very non-polar molecule. Why do I say that? Well, the electronegativity of carbon is going to be about 2.5, and the electronegativity of hydrogen is going to be 2.2. Now, the values range from 0 to 4, very arbitrary, fluorine being the most electronegative. Now, with carbon having an electronegativity of about 2.2, and hydrogen of about 2.5 and 2.2, we're going to call that about equal. So the bond between hydrogen and carbon, the electronegativities are the same. The hydrogen wants to keep its electrons just about as much as this carbon does. So this bond, these two electrons that I haven't drawn in, there you go, two electrons, are going to be about equally split between this carbon and hydrogen. If you want to get picky, they'll be tending to stay around the carbon just a little more. However, for most books, probably your class, just saying that this is a non-polar bond is going to be completely acceptable. And by non-polar, I mean that the electrons are going to be equally split between this carbon and this hydrogen because the electronegativities are about the same. The nucleus wants to hold on to its electrons about the same in carbon and about the same in hydrogen. Now, let's do an example of water. Now, unlike this molecule, oxygen and hydrogen are very far away from each other on the periodic table. And I'm just going to tell you the electronegativities are very big. I'm not going to give you the exact ones, just so we can get this going a little bit. So, in this example, oxygen is going to be very electronegative, hydrogen's not. What does this mean? Oxygen is going to want to take these two electrons. If there's two electrons in this bond, oxygen is want to suck these electrons closer to its nucleus than hydrogen. So the electrons are going to reside a little bit closer to the oxygen. Well, what does this do? It's going to be over here as well. Well, if you have electrons, which are negatively charged, closer to the oxygen, you're going to gain just a slight negative charge on the oxygen and a slight negative charge on the hydrogen. Because the electrons are closer to the oxygen, electrons are negative, hydrogen is going to have two electrons still, but a little further away. So you're going to have a slight positive charge. So you're going to have a slight delta charge, positive charge on the hydrogen. Same over here, and you're going to have a slight negative charge on the oxygen. To draw this representatively, you do that. And you can do it with both, because they're both split. Where you have a slight positive charge, I like to think of this as just a positive charge right there, on the hydrogen, and you have a negative charge that points towards the oxygen. Let's do one more example, just in case if I didn't do that clear enough. Boron and fluorines. Now, which of these is more electronegative? Well, easy one. Fluorine is, because I told you that's the most electronegative. So, the electrons are going to want to stay over here in our molecule, where fluorine is going to hug these electrons a little more than the boron is. So over here you're going to have a delta negative charge, and similar with all of these. And then how do I draw it? Well, you represent it by drawing the positive charge at the boron, and then the negative charge is going to point towards the most electronegative, which in this case is fluorine. So let me finish drawing that. And this is how you represent bond polarity. And in this case, this molecule right here, you're going to have this fluorine, and this fluorine all equally spaced from this boron. So you're going to have a negative charge over here, a negative charge here, and a negative charge here. The net polarity of this molecule is not going to be polar. Well, why do I say that? Over here, we have nonpolar bonds. Here we do. We have polar bonds if you look just at this boron and just at this fluorine. That is a polar bond. However, all these fluorines are going to be equally split. And let's say that's the boron in the middle. When you have a negative charge that direction, a negative charge that direction, and a negative charge that direction, it's actually going to be a nonpolar net charge on the molecule. This molecule is not going to have a big negative charge over here and a big positive charge over here. The negative charges are all split, meaning it's going to be overall nonpolar molecule, even though these bonds, all three, are individually polar. So over here, let's look at water. This is going to be a polar molecule. Well, why do I say that? Over here, you have a hydrogen that's going to be slightly positive hydrogen. And then over here, you have two lone pairs of electrons. These are going to be placeholders. So, like I did over here, our oxygen is going to be the dot. And then you're going to have positive charges now. I'll represent it by that. And then you still have these electrons over here that still take up space, and we can't figure out, and we have to remember the molecular structure. So in this case, you're going to have a positive charge over here, and a positive charge over here, and a negative charge, a larger negative charge, because you have two pairs of electrons. So when you have positive charges, positive, and negative, you're going to have a polar molecule. The electron density is going to be closer to your oxygen, meaning that this side of the molecule is going to be positive, or negatively charged, and this side will be positively charged, giving you an overall polar net charge. Over here you're going to have a nonpolar net charge on the molecule. Even though polar, polar, and same with over here, all these individual bonds are polar. However, when you look at the big picture, when you look at the molecular structure of the molecule and the bond polarity, when you look at the electronegativities, bond polarity becomes nonpolar net, polar net.